Hello, my name is Anatoly, and I'd like to present you my research today on topic consolidation sensor framework for challenging material characterization problems. Consolidation is a central process in composite manufacturing. It affects defects formation like fiber path defects, resin defects, and so on, and the compressibility of the materials, meaning that dimensional tolerances are affected as well. Consolidation is driven by the resin flow, and there are a number of different resin flow models, such as shear resin flow when resin flows transversely to fiber direction, causing a fiber shift, or percolation resin flow when resin just bleeds out of the composite. The problem is that we don't know in advance which process is happening inside the material under the particular processing conditions. And also these processes may occur concurrently and may be interconnected with each other. The standard characterization process is basically a compression test of the compressive precursor where we apply a certain load and study the compaction response of the material. As I said, we have a number of different resin flow modes, and normally they are represented in the form of differential equations, where in simplified form, we have a force component and a component which represents material parameters such as viscosity, permeability, and so on, depending on the particular material model. And we don't know which one exactly is valid for these particular conditions and this particular material. So what we do, we conduct a simple test, compression test, and we study the compaction response by trying to fit each of these models to the compaction curve and see if they can describe the process. As we can see here in this example, we have two models, model A represented with the green curve and model B with the red curve, which show nearly indistinguishable performance. They both can fit the compaction curve. So how do we pick which one is right? Well, we also have a validation stage where we try these models against the more sophisticated load schedule. And as we can see here, the red model is completely incapable of outputting a feasible prediction about changed material behavior, while the green one still operates well. So the way we conduct these fitting is by implementing a two-step parameter extraction routine. The first step is simply a brute force search with the low grid. We don't want to spend too much time on that. With the low grid parameter. And the reason for that is that we want to find a starting point for our parameter set, which we'll use for the secondary stage. That's basically for optimization of choice. We can use the least square method on Eldermead or whatever they want. And that's how we find, we fit one of these models. And we can repeat this process for every single model which we consider, because as I said before, we don't know, we don't define model in advance of the experiment. So the next question is how to conduct this characterization test. So the first option is to conduct a data-rich testing program. Here we conducted a compression test on the crucifix sample. We had 8 tests which covered different various number of load rates and load amplitudes, and we randomly picked 3 tests to use as a training set, and the rest will be used as a validation. We can train our models on each of these tests separately, or join them in a couple data sets, or join them all together. As we can see, if we review the largest data set, it performs well on training stage as well as the validation stage with a little offset. If we consider just one set, it performs well on the training, but shows a significant offset on the validation. And on the comparative performance chart, we can see that it shows a 30% error, meaning that this program is not data rich. We need something else. So the next approach is a data-driven compaction test. Basically, we don't define the testing program in advance. We let the algorithm do it for us. We have a model library of models, which, as I said, differential equations, and we study the compaction response in real time. We study each of these models simultaneously, and we do have a ranking of which model performs better. And based on that, we can construct a load schedule for the next load step, by picking an option from one of the options. And we can see how the program is constructed in dynamics. We have a compaction response here with the prediction for the next law step. We have various options for the next law step, and we can have a comparative bar chart for each of the models in the library. We can see which models perform better and how it changes throughout the experiment. And that's how we, in the end, we have a completely data-driven by consolidation testing program for our composite. Thank you for your attention. If you have any questions, you can email me. Thanks.